Hello again. So to talk about today's lab, we're going to do a thermal analysis using Excel, similar to what we did with the diesel cycle, the thermal analysis we did a couple of weeks ago. But this time we're going to be doing it on a combined cycle plant using this as our support, our basis for calculation. So we're going to be using real performance data from main independence, the power plant at VZ, and we're going to analyze the Brayton cycle. That's the one for gas turbines, in both real and ideal Brayton cycle, and we're going to calculate the heat transfer through its heat recovery steam generator. After this, we'll do a very brief kind of thermal analysis of the Rankine cycle. So we'll see what type of boost to the power plant performance or efficiency we can get from that recovery. Just a quick overview of gas turbines. So there are two main gas turbines. You've got a jet engine like this one for thrust, and you've got this power propulsion turbine. Generally, these kind of turbine are attached to a generator head shaft, or to a shaft attached to a propeller shaft, such as a turboprop plane or a ship. And that is the main difference with a jet engine like this, which where there's just the turbine itself and which is focused on thrust. The basic overview, here is the our intake. So we get air coming in that will go through a number of turbine blades or stages of compression to increase the pressure and compress the air, right? Then the air will go through the combustion chamber, otherwise called combustor, and the air and combustion product goes through and expands through a power generating turbine blades. You see here those blades, and then get to the exhaust. For a jet engine, that power generating turbine drives the compressor. You see there is a shaft linking the power turbine and the compressor. For power propulsion engine, the power turbine also drives the compressor, same way, but its main function is to produce work to the propeller or generator. Here's an animation, a GIF, showing how our gas turbine works here. So let's look at how this cycle actually works. So we've got PV and a PV diagram here and a TS diagram. So remember, this is PV, so pressure versus volume. So if we were to find the area under this curve and inside this cycle here, what do we get? Work, right? We also have this TS diagram here. This So it's here to try to help you determine what type of process each of these are. So we've got our cycle here. You can see 1 to 2, 2 to 3, 4 to 1. Same here. And back to 1. And you can see the coordinate with numbers up here on these two cycles. So if we look at this diagram here, we've got our fresh air coming in to our compressor, to our compressor side. It goes through compressor, so 1 to 2 here, and here on the TS diagram. You see that the entropy is constant entropy. So what type of process is that? That's the isentropic process. So what we are basically doing here is an adiabatic compression, right? So we do that adiabatic compression, then we get to state 2 here, where the combustion happened. So that's where we are putting the heat and the fuel, right, into the combustion from 2 to 3. So you see it in. We get heat into our system to get to stage 3. You will note that it's supposed to be at constant pressure. It happens quickly enough so that the pressure ideally does not increase. But we get an increase in temperature, obviously. You can see that here there is an increase in temperature. And we also get some increase in volume. Here you can see 2 to 3, there is an increase in volume. And also, so when we get the turbine going from state 3 to state 4, that's an expansion through the actual power turbine, right? So we get another isentropic process, 3 to 4, 3 to 4 here, and then 4 back to 1, 4 back to 1, exhaust to fresh air. That's our heat out, and that's our exhaust here. And then we just complete the cycle. But in reality, especially for a jet engine or thrust gas turbine, it's an open environment here. So we can assume that the environment, the sky, in this case, is big enough that if we were recycling that air, it would go through some sort of cooler and come back to state 1. So in brief, it's the cooler is really just the environment, right? So we're exhausting that hot gas into the environment, and and our air intake here is also fresh air from that environment. So we can say also that this is done at constant pressure. Okay, so basically, what we are going to do for this lab is use that ideal air standard Brayton cycle. So that means that we are going to assume a constant CP throughout this, which will make the analysis a little bit easier. We're going to assume isentropic compression and expansion through our compressor and turbine. And we are going to assume constant pressure heat exchange, so that basically means that there is no combustion, even though there is. Confusing, isn't it? But actually using an air standard means we are basically just analyzing the air going through the system. So we can't technically take into account the fuel and the combustion, because combustion gases are different than fresh air, obviously. They've got particles, including excess hydrocarbons and other things. But to try to do the analysis on the actual exhaust is very complex. That's, by the way, one of Professor Sarnaki's field of expertise, and as he's also a combustion engineer. So now, remember that we are simplifying that. It's an air-based analysis. We are not considering the nature of the exhaust gases. So now for the efficiency, remember, is whatever work we get in, whatever work we are getting out, divided by whatever heat we are putting in. Even though we are not saying we have combustion, but we are still putting fuel in the system, so we have heat. So, well, when you look at the efficiency here, W net work, so that's what that network here. It's going to be the difference with whatever work we get out of the turbine, and minus whatever energy it takes to spin the compressor, right? Again, remember there is a shaft. It's directly coupled. If we go back one slide, if I can, you see there is a shaft. The turbine and the compressor are coupled. So this is where you got your the explanation of that. W compressor, W turbine for the network. The difference between the two, the work of the turbine and the work of the compressor. Okay. Oh. All right. So you see what to expect. So, okay, here is what in reality, the real, we are talking about the real turbine cycle as opposed to the idealistic one. So here's what in reality happens inside of that gas turbine cycle. So a real analysis does include the inefficiencies of our heat transfer, or the combustion, or the inefficiencies of the compression, inefficiencies of the expansion. So what really happens, and it is easier to see on the TS diagram here, actually instead of having these constant entropy processes here, instead of having those constant entropy here, you've got some pressure drops, especially during heat rejection. So what really happens is we get this kind of a distorted, skewed look here compared to our smoother looking straight line TS diagram on that side, on the left. it actually becomes from 1 to 2A up to 3, and then 3 to 4A, and then back. So these two, the 2S and the 4s are the point from our ideal analysis here, but we actually get some change in entropy from each of those, basically. They are no longer isentropic. There is some change of entropy in the real world of gas turbine. Okay, so that's in reality what happens. The other thing that the real system takes into account, is what happens with combustion. So exhaust is not clean, there is additional mass, you do get some particles, deposits on surfaces. So whatever your inlet mass flow rate is with your air and your fuel coming in, it's not exactly what you're getting out for the exhaust. It's close, but not quite the same. So in a real analysis, that's part of it, and that's why I was saying that it's very complex when you deal with exhaust gases and closer to the real cycle. The CP of the air is not the CP of exhaust. It's a different animal. You see, different. In brief, we are using an approximation, but the point is gives you a rough idea of what to expect. Okay, so you know that the second law talks about Carnot, because remember Carnot, which is the maximum theoretical efficiency, is really the efficiency for a reversible process, right? So you have your high and low temperature reservoirs, like this, and that's really all Carnot is about, that formula here. So it looks like it, but it's a little bit different from what we saw for the heat pump and refrigeration lab. That was called COP, not efficiency. And then there are a few other useful equations that will help you get through this during the lab. We have actual and ideal equations, essentially. So if we know what the change in enthalpy is, we know what the mass flow rate, Cp, and our change in delta T. Here we can figure out then what that actual change in energy, or what our workout is. Is that, yeah, right? But when we do the ideal, we get this T2 prime, right? So these two temperatures are things we are going to measure. Now, the T2 prime is one we can calculate. So we are going to use that polytropic equation using the measured T1 and our pressures as well, P2, P1, with our C sub P, C sub B ratio, which is going to turn to be gamma, our specific heat ratio. Then we can calculate that T2 prime, considering that the mass flow rate and the CP don't really change much. Then finally, if we want to calculate the compressor efficiency, it's a ratio between what you know that actual energy is, or work output, versus the ideal. So you see here, work, ideal, compressor work, ideal, compressor work, actual. So when you divide this by this, you can see that that the M0 CP cancels. What's left is just the ratio between the temperatures here. You just need to calculate T2 prime based on this. Easy. So that one was for the compressor, but this one is a turbine side. So it's the same thing on the turbine side if we know what T4 here is. It can be measured, and it's just the exhaust temperature. ME, the mass flow, you will notice, is no longer the one of the air as on the compressor side, where it was M0 here. It was for the air because it's on the compressor side. That mass flow here, ME, is for the mix of fuel and air. Note that look at the efficiency, they look similar, but be careful. If you look at the at this one here on the compressor side, the two efficiencies are backwards from one another. So now we are getting to the heat recovery aspect, which again, the gas turbine produced energy, and the byproduct, the gases are being used in a steam generator. They are used to basically heat up a boiler or a heat exchanger, I mean. So when you get into the heat recovery unit of the plant, the heat recovery steam generator, or HRSG, there are three stages where you get your low, intermediate, and high pressure. All those stages are essentially three ranking cycles, right? But we are going to simplify this whole thing. Instead of doing three different analyses and all this, we are just going to assume that the whole thing, the whole HRSG, heat recovery steam generator, acts like just like the simple counterflow tube and fin shell heat exchanger. So that's an assumption we are going to make here, and it's basically just a big heat exchanger. We are just heating up water, making steam, and that's what it is. So we're just going to simplify the whole thing to a heat exchanger. So doing that first law analysis on the heat exchanger, remember this is just a change of enthalpy. It describes the difference between our heat and work energies. So this MCP or M.CP C sub P delta T here is really the definition of that change of enthalpy. Because we are not, remember, we are not getting any work out of a heat exchanger, right? So that heat coming in from your turbine is heat available for the steam, right? Here you got T in, gas turbine exhaust temperature, and T out. It's the heat recovery steam generator temperature. So, how are we going to figure out figure out that heat and all, and work on some of this stuff, or figure out the heat transfer coefficient? We are going to use this heat transfer equation here, which is a classic one. So you see the various factors here are U, and U is called the heat transfer coefficient, and this one depends on the type of heat exchanger, shell tube, plate heat exchanger, depends on how many passes, how many plates, etc. And it's going to be given here. A is the wetted surface area. That's the surface of tubes and fins, and that's the total surface area for the heat transfer. And otherwise, we are going to use the LMTD, another factor here. It's just the LMTD is the log mean temperature differential, and it's a logarithmic average of the temperature difference between the hot and cold feeds at each end of the exchanger. So if we explain that a little bit more, so all that LMTD really is we have our inlet side here, we've got our outlet side here B, you've got your side of your heat on your heat exchanger basically is A and B, that's the two sides. So for a counterflow, which it is here, you've got an in and out occurring in both sides A and sides B. Okay, so for this one, we've got for this example, we've got our exhaust coming in at 620 degrees Celsius, right? Then we're putting the heat out, and it's coming out at 92.8 degrees here. But we have our water coming in at 48 C on the other side, and that's heating up. It's putting the heat out of that exhaust, and it heats up at 570 degrees Celsius. So, in brief, to calculate the log mean temperature differential, you just use this equation right here. You just need this equation. This delta TA and delta TB, or it is just the difference between the temperature on side A and side B. Okay, so that temperature differential difference between the 620 and the 570 is delta TA. You plug in that in there, here, and then you take the difference between on that side 98.2.8 and 45.8, and you plug it in there. And then the same thing, oh, yeah. Yeah. And then just make sure you put it in your calculator properly. That's a question of not inverting things. So, well, everything you need to do the lab, equation-wise, is in this presentation. So please bring your laptops with you to the lab. Just a quick word about the lab itself. Let me put that down. It's on Canvas for you to download. It has a number of measurements taken. As you can see here, they all come from actual data from main independent station operating at intermediate load. So we have our T1, P1, P2, T2. That's for the gas turbine, the Brayton cycle, everything is there. We have pressures P1, P2, our network coming out. Network, remember what it was? The lower heating value of the fuel that's injected, and LHV, the K value, which is gamma, actually. Remember gamma? C sub P. We have temperatures coming in and out in the heat recovery steam generator HRSG unit with a heat transfer, and the coefficient U is given here. The heat exchanger coefficient, as you remember, and the work that we are able to get out of the turbine, which is coming out of that Rankine system, because essentially you're creating steam to run a steam turbine to get an extra energy boost or work out of the whole power generation system. So here's the diagram of the turbine as we saw it, and here an extract of the questions you're going to use. So we are not going to print off this lab, just download it, and what you'll do is just start creating an Excel file where you will enter all of what you know here, your nodes here, and then just start calculating these answers for all these questions, basically. Okay, so we'll be there in the lab to help you get all this done, so we'll see you in the lab. Take care.